Let's talk about text-to-speech programming. Along the way, we'll also mention lip syncing. Now, text-to-speech programming is not used a lot in computer games, and one of the reasons may be that in the past, the text-to-speech voices are the automatically generated speech voices that came with computers, especially PCs, generally tended to be low quality and sort of robotic sounding. And so for that reason, developers probably didn't like them. And so even today, text-to-speech might not necessarily be the best use of speech audio for a computer game, unless it was, for example, used in the interface or something like that. So not, for example, a character talking. Even so, I think that there is a very good use of text-to-speech in game development. And by the way, let me mention that text-to-speech is simply the ability for a computer program to generate speech audio from a string. So you see this example program here where we're calling a function called speak, and we're just plugging in a string, and it's going to speak that string over the speaker, so it's going to generate the audio dynamically. Now, one of the things I think can be really useful in game development as far as text-to-speech goes is, let's say that you're creating a prototype of an application and there's going to be a lot of spoken dialogue in your game. Now at some point you may want to hire voice actors and get them in the studio and record the different things that they're going to say, and then you're going to get that in your program and play it back. But initially, when you are creating simply a prototype of your program, before you have all that audio data recorded, you may just want to plug in text-to-speech into your application to fill in those places where you need to have audio. That way, you can continue on with the program. You can test the program, you can beta test the software, and then later, when you're satisfied that you really do want that particular audio, then you can go and get a voice actor and have them record it, and then you can replace the text-to-speech with the actual voice data. So I think that text-to-speech could play a really important role in game development, especially creating prototypes. Now, to get text-to-speech in your program, first of all, you need to go to the internet, and I would search for in a search engine, Microsoft Speech SDK 5.1. And so here it is. You'll see the download button, and just download that and install it on your computer. Under system requirements, you'll see that it supports basically every Windows operating system. Windows 7 is not listed, but it works on Windows 7 because I'm using it on my computer, which is Windows 7. I've not tried it on Windows 8. If you have a problem with that, please let me know. Now, we sometimes refer to this software as SAPI, Speech Application Programming Interface, so SAPI. SAPI's been around since about 2009, or that's when this particular download is dated. So this is a little bit older API. Microsoft has some other APIs for speech programming, but I find this is one of the easiest ones to use, especially when you're working in a C++ program. So look that up, download that, get that on your computer. Now, in terms of what you're going to need, or what you're actually going to use out of this toolkit, because it actually contains quite a bit of software. All right, let me describe that. All right, so after you download it and install it, you'll have in your program files directory the Microsoft Speech SDK 5.1 folder, and you'll see a lot of folders inside of that. And again, as I mentioned, there's a lot of software in here. Most of that we won't use for what we're going to do. which is simply to integrate text-to-speech into our applications. In particular, there's a live directory, and you'll find one static library, sappy.lib. And so that's something that you need. And you'll also need the include directory. Now, this is not the original include directory. This one is the original one, but I had to make a modification. It turns out there was a bug in one of their headers, and so Microsoft recommended a fix, and for some reason they never added it to this download. So this is something you have to do yourself, but it's pretty easy to use or to do. And if you look at the include directory, there is a header file called sphelper.h. And I've saved the original version here, although there's no reason you can delete that if you want. And you're going to need the updated sphelper.h. Again, it's not in the download. However, let me show you where you can find it. In your Dev 2012 W7 folder, just go to Libraries, Audio, TTSW7, and then you'll see a folder called Fix Sappy Header. And this is the updated sphelper.h file. Just copy that into the Sappy include folder and overwrite the file that's already in there. And then you'll have the correct header file. Now, as I mentioned, the header directory, the include directory, and the live directory are really the only ones that you need for developing. You can probably get away with only having those. However, if you don't have access to those files already, then you'll have to go ahead and download and install the full SAPI anyway in order to get them. But if you're working on another computer, let's say that you're moving your development environment from one machine to another, it's really only necessary to work in SAPI to copy over the include and the library folders. Okay, so the first thing I recommend you do this week, and you do it right away, so if you have any problems you can figure out what those are and try to fix it, is you go ahead and find the Speech SDK on the internet, download it and install it. And then again, as I mentioned, right after you install it, go to the include folder and then replace the sphelper file, header file. Okay. Now, when it comes to SAPI, the interface is not necessarily difficult to use, but I don't find that it's as easy to use as I would like it to be. So for that reason, we've got in our Dev 2012 W7 folder in audio, we have a interface library or a helper library called TTSW7. So let's look at that project. Okay, so what we've got here is going to be one CPP file that has the code in it, and this code is going to interface to SAPI. So it'll make it a little easier for us to write code that talks to the SAPI interface. And for the most part, you probably don't need to look at the C++ code, but let's look at the header file. Alright, so you see we have some functions and some constants. Now, first of all, we'll have some voices. Now, you should have on your computer the Microsoft Mary, the Microsoft Mike, and the Microsoft Sam voices already. And if you don't, then you'll get those when you install SAPI. I also on my computer have software called AT&T Natural Voices, and so I have some additional voices on my computer. This is paid software that I purchased some time back, and AT&T created some very nice human sounding voices. They're really, in my opinion, much better than Microsoft voices, so I like to use them when I'm programming on my machine. And certainly you can find those on the internet somewhere if you want them. But they were several $100s, so you might want to just stick with the free voices, the Microsoft voices. Next, we've got some flags whenever we make a call to speak, we're going to have the opportunity to plug in some of these flags. Now, the default will be none. Okay, and then we'll have a flag called sync. And let me go down and let's look at the speak function right here. Notice when I call the speak function, I'm going to plug in the library or the TTS engine, and I'm going to plug in a string that I want to use, that I want it to speak, and then I have the option of plugging in flags. The default is, which is none. Now, what exactly sync does is the following. When I call speak, it's going to start speaking what's in the string, but the function itself is going to immediately return. So it's going to that's what we call asynchronous. So it's not going to wait for the audio to finish speaking. This function is going to return immediately. Now, one of the problems with that is you may want to wait for it to finish speaking because you may have some other processing that you want to do. Maybe you want to speak something else, or you want some text to appear on the screen, or something else to happen in your program. So you won't want to wait for the speak call to finish up. So if that's the case, then you can use this flag called sync. So when you call TTS speak, it'll speak, and then it'll wait for it to finish speaking before it returns control back from this function. So if that's what you want, then you want to use sync. The other thing about speak is, if you were to call speak twice, this function called 2 times consecutively, let's say with the first sentence and a second sentence, it will speak both sentences one after another. But if you were in a situation where, let's say you had a very long sentence, I mean almost like a paragraph that it was speaking, and for some reason in your program you decided you want to interrupt that, you want it to stop that, well, you can call stop, but let's say you wanted to say something else. So if that were the situation, then you can use this flag called purge. So if there's any audio that's being spoken currently, or that's queued up to be spoken, then you can just purge those pending speak requests. You can also use these flags together if you want. So that might be something that you want to do. So in other words, you want it to be synchronous. You want this function to return after it's finished speaking, but you also want to purge any pending or current speak requests. So in that case, you might use the flags together. And I'll show you an example of that. As far as the other functions goes, notice we have a data type called text-to-speech. So that's going to be our handle to the engine. So we've got a function to initialize the TTS engine. We've got a function to free the engine when we're done with it. So that would be typically before you exit out of your program. And the initialization would be once at the beginning of your program. Then we have the call to speak. If we want to stop speaking, a current speaking request, if we wanted to stop in the middle, we can call stop. We can also set the voice. Now you wouldn't want to set the voice in the middle of speaking. This is something you want to do before you call speak, typically at the beginning of your program, although you can change voices during your application if you want. If you want to set the volume, and you can only lower the volume. So think of the volume as always being 100%, but if you wanted to lower it below 100% volume, then you can do that. You can also set the rate. So if you want it to speak faster, use a positive number, or you want it to speak slower, then you can use a negative number, so you can adjust the rate that it speaks. You can also have it speak to a WAV file instead of to the speakers if you wanted to store that audio for use sometime later for whatever reason. Okay, so now that we know how that works, let's take a look in an example application. So in the same audio folder, there is a program called TTS test. And so I have it here. And so let's look at the main function. First of all, this is a console application. Now, there's no reason why you can't use the TTS engine and this TTS library in a graphics application. certainly that's the case, and I've used it that way myself. But let's look at it in the case or the context of this very simple console application to understand how it works. So we're going to start off printing a string to the console, and we're going to initialize the engine. We're going to set the voice to, and I'm going to use AT&T Audrey here, and I'll play that for you, and then we'll switch it over to a Microsoft voice. Then we're going to call the speak function, and we're going to use sync because we want it to wait and until it's finished speaking before it returns. Otherwise, the program would exit out too fast, and we wouldn't have a chance to hear what it says. Then, just for the heck of it, we're going to speak the same thing to a WAV file. And then finally, we'll free the library before we exit. So let's run this and see how it sounds.
Hello, how are you today?
Okay, so that was the AT&T voice. Now let's switch it to the Microsoft, one of the Microsoft voices. And if you can't remember where that header file is, let me show you a trick. Any files that this project depends on are listed in what's called external dependencies. So you can go and browse and try to find that header file, or you can do it this way. So let's click on external dependencies. They're all in alphabetical order, and we find it right here. Okay, so I'm going to pick the Microsoft Mary voice, and let's try it.
Hello, how are you today?
Okay, so it's a little bit different, but certainly it's understandable. Next, let's plug in another speak call.
Hello, how are you today? Today is Saturday.
Okay, so there we have two different pieces of audio. And notice I'm using sync on both of them. Now let's suppose on the first one I didn't use sync. Let's see what happens.
Hello, how are you today? Today is Saturday.
Okay, so that worked. Well, what happened was we called the first speak, and so it started speaking the first sentence, but it immediately returned back to this function, back to our code here, in which case we called another, we made another call to speak. Now, by the time we made that call, it wasn't finished with the first one, but what it did was it queued up this second sentence to be spoken after the first one is finished. And then, using sync, now it's going to wait to return until it finishes speaking the second sentence. So that way we're able to hear both of them. Now, if I wanted to, for example, purge the first one, let's see what that would do. Okay, so you notice how we didn't hear anything. Alright, so what happened there was we made a call to the first one, and it may have started speaking, but it's going to immediately return, and then we made a call to the second one, and by saying purge, it's going to purge the first one, so it gets rid of the first one, and then it starts speaking the second sentence, but since we don't have sync, it immediately returns back to us, and then it's going to exit out of the program before it really had time to speak. So that's why you didn't hear anything. Let's put purge together with sync. Alright, so you'll notice, and let me get the header file open again. Okay, here's our flags. And this is an enumeration, and in C++, enumerations are integers. So let's put sync and purge together. And these are basically bit fields. So notice hex 2 and hex 4, those are individual bits, but they're different bits. So we can OR these together. Although you'll get an error when you do this, because the parameter that's expecting is of type TTS speak flags. You notice this enumeration is called TTS speak flags. So it's an enumeration of these three integers. An enumeration is basically a way of creating a set of constants, integer constants in C++, in a listing form. Alright, so let's cast those two. Speak flags to keep the compiler happy. Let's run it now.
Today is Saturday.
Okay, so in that case, we only heard the second sentence, and why was that? Alright, so we played the first, we did the first speak, but since we didn't use sync, it's going to be asynchronous. In other words, it's going to return immediately from that function call. Then we use the second speak call, and in that case, we're using purge, so it's going to purge the first one. So we won't even hear that at all. And then we're going to use sync, so that way it won't return until it's finished speaking the second sentence. Alright, so that's just a few examples of how to use this library. Generally, it's pretty easy to use. I'm going to put it back the way it was. Let's spend a little time now and talk about lip syncing, because that is a technology that's many times used when you're using speech in a computer game. A lot of times in a computer game, you not only want to have a voice talking, but you want to have a 3D character tied to that. So in older games, you may see a 3D character in a game, and then you hear a voice, and so the voice and the character are tied together. But what really makes it a lot better is if the lips move. Again, in some older computer games, whenever a voice of a character was talking, sometimes they would just have the lips moving up and down, and to kind of give you the effect that the character is talking. But the lips wouldn't necessarily be synchronized with the audio. And these days there is a way to do that. In the Maze building at Lamar, in the game development lab, we have software installed called FaceGen Modeler. You can find it at www.facegen.com. They have a demo, a free demo, and then you can see the paid version is not cheap, but it is a very nice program. And FaceGen Modeler allows you to create faces either from photographs, or you can create random faces by using different characteristics like age, race, so forth. A lot of different parameters that allow you to control the generation of these faces. Unfortunately, they don't have a full body program, but they do have this face generation program, and it will output a lightwave model. And if you wanted, you could take the model and then put that, attach it to a full body. Now, what's interesting about the model that's generated by this program, FaceGen, when you export it to Lightwave, you get a set of morph targets. And let me show you those. Alright, so here's a model that was exported from FaceGen. And I took the time to color this model so you don't normally get a texture that looks like this. But what I wanted to show you was take a look at the vertex maps panel and under morphs. So they have different expressions: anger, disgust, fear, sad, smiles, surprise, and so forth. So as you saw last week, controlling morphs in your program from a lightweight model is very simple, very easy to use. Now, one of the very interesting things is, as part of these morphs on these faces, we have what's called, or what FaceGen calls phonemes, but what are really typically in the industry called visemes with a V. And what visemes are basic units of speech, visual units of speech. In fact, phonemes are the basic units of speech, but visemes are the visual units. So let me explain that. When you're speaking a word, for example, that word can be broken down into phonemes, basic parts of speech like ah, o, r, s, different sounds. So there are about 39 different phonemes. However, those phonemes, those different sounds, sometimes for a set of those, they have the same visual appearance, uh, when they're being spoken. So while there are about 39 or 40 different phonemes or basic parts of speech, the corresponding visemes, the visual units of speech, which I'm demonstrating here, that is a smaller subset. Okay. So like this particular morph here, that might be the ah sound, or it might be some other sound that is different, but your mouth is in basically the same position. So how would you accomplish lip syncing a character like this? Again, uh, importing a Lightwave model in your program and controlling the morphs is relatively easy, as we saw in the last assignment. But knowing which of these visemes, and again, uh, FaceGen calls them phonemes, but they're really visemes because these are the visual units of speech. Controlling these visemes would be another matter. So let's talk about that process a little bit. And here's a quick look, by the way, at 16 different visemes, so different visual parts of speech. Okay, so first of all, you would need to know to drive the lip syncing on a character using the morph targets, you would need to know what's being said. Now, if you just have an audio file, then you'll want to listen to it and understand what's being said and then write it down. And then basically you're going to use that as data. If, for example, though, you're using text-to-speech, then notice you already know what's being said because that's what you have to write or type in your program. All right, so with text-to-speech, it turns out to be very easy because you already know what's being said. And if it was audio, well, you'll have to listen to it. But there again, if you're in a game development environment, you're going to know what's being said in the audio. So either way, you're going to know what's being said. Now, what you'll need to do next is take the individual words that make up the sentence, let's say what's being said, and you'll need to translate those into phonemes, into the basic units of speech. One of the easiest ways I've found to do that is using a tool. There's a free tool, or tools maybe is not the right word, but more of a reference. The Carnegie Mellon University Pronouncing Dictionary, so the CMU dictionary. And this contains about 100,000, actually it's 134,000 now, English words and their corresponding phonemes. So you can find it online here, and you can use it royalty-free in any applications that you create. Okay, so back to your Dev 2012 W7 folder. Let's go to Libraries, and we'll look at a folder called Vocab. Actually, let's look at Vocab Test first. And here you'll find an earlier version of the CMU dictionary. And so let's take a quick look at it. Okay, so anything that starts with a pound sign is a comment. And let's just jump down to, say, the middle of it somewhere. Okay, so you see the word on the left-hand side. Each of these words is listed. You've got one word per line in the dictionary. And so, for example, boy, the word boy is made up of the phonemes B and OWI. And let's look at another one, boycott. That's made up of a B, another phoneme called K, another one AA2, and then a T. So there's 1, 2, 3, 4, 5 different phonemes that make up this word. Again, these are the basic parts of speech, of audio. This is what you hear, not what you see. So the phonemes are what you hear, and there's about 39 of these. Now the visemes, the visual units of speech, again, some of these phonemes have the same viseme, so they look similar. But your first step would be to figure out what the phonemes are. And so that's where this CMU dictionary comes in really handy. You could read this in your program and store it in basically in a database in your program, and then using a binary search technique, you could easily look up a word and then extract the corresponding set of phonemes. So if you have a sentence like this, what you'll want to do is you'd want to look up each word and then come up with the phonemes for that word. Okay, so let's look at this library called Vocab. And you won't do a project with this code, but I wanted to show you how it works, so at least you'll have an understanding of the technology for how to use either text-to-speech or even real audio, human audio, in order to drive a 3D character using the morph targets. Alright, so I'm going to open this vocab library. Okay, and there's a header file and a CPP file. Let's look at the header file. First of all, we've got some data definitions, but you'll see listed the 39 phonemes. Okay, and so these come right from the Carnegie Mellon Dictionary. So here's the double A, AE. Some of the other ones we were looking at, I think, were the OY, which is here. It's number 26. There's an example and a translation. So basically, we've got these 39 listed as a constant. Now, how these correspond to visemes that's a little bit different. Again, there are 39 phonemes. Now, what about FaceGen Modeler? Remember the program Modeler that we looked at? It does a great job of generating faces, but it only comes with 16 visemes, and they are listed here. So, once you translate your words into phonemes, then what you need is to map the phonemes, of which there are 39 different ones, into the visemes. After you've mapped them into the visemes, then you could use that information to drive the lip syncing on a face. So let's see how this software might help. And I should mention that I wrote an article for programming or game programming Gym 7 a couple of years ago, in which I described this process, which is the process of using text-to-speech to drive the lip syncing on a game character. So that might be something that you want to check out in the future. In any case, this is a library and we can initialize it, and we would initialize it with a file name, and guess what? That would be the name of the CMU dictionary. So this is code that's going to read in the CMU dictionary, and when we're done we'll free up the library. And so we've got a function here that translates an individual word using this vocabulary, basically using the CMU dictionary. And here's a string, the word that we want to translate. And so it'll come back with the number of phonemes that it generates. Like for example, in boy, I think there was only 2. And then a string containing these different phonemes. So it'll be a sets of these. Okay? All right. Now again, having the phonemes is not really that useful. What we'd really like to have is the visemes. But here we have another function, translate phonemes to visemes. So once you get the phonemes back from translate word, you can call this function here and pass it your phonemes and the number of phonemes. So that's what this n is. And it's going to come back with a set of visemes. Okay, so that is going to allow you to drive a face on a 3D character. Now, you need a little bit more information than that. For example, if we looked back at the string that we had here, hello, how are you today? Sometimes some of these words, they may take longer to say than other words. For example, hello is several syllables, so it takes longer to say that word than the word you, which is only one syllable. So in addition to understanding what visemes make up this sentence, we are also going to need some timing information so that we would know when to, for example, when to start playing a particular viseme or morphing a face using a particular viseme, and when to turn it off. And so the timing information is also going to be important. All right, so that's what this next function is going to allow us to do. So vocab lip sync, again, we're going to use the vocabulary that we've read in, and we're going to plug in an input data structure, and then we're going to get back an output data structure, and that's going to be allocated by this function, so you want to be sure and free that memory up when you're done using it. All right, so I won't generate the full I won't demonstrate the full lip syncing because of time constraints, but let's at least look at the process of translating words. So for that, I'm going to go to another demo, vocab test. So let's go to this project, and there's a little refresher file here that shows me the different phonemes that are in FaceGen, which really are visemes, but FaceGen calls them phonemes. Okay, so these are the visual units of speech. And these are the things that you'd want to use to drive a 3D character from FaceGen, for example. So let's open this project and see how it works. Okay. So first of all, we're going to load the dictionary. So you have the call to vocab init, and we're going to use the CMU dictionary. We're going to load all 100,000 of those words. Next, we're going to call the translate word function, and if it's a word that's not in the vocabulary, this function will return false. If it's in there, it'll return true. So we're going to plug in the word market, and we're going to pass it a pointer to an integer in and a pointer to a set of phonemes. Okay, so that way it can fill up those data structures for us. And if that word is found, then we'll print out that the word is found, and then we'll print out the set of phonemes that that word consists of. Next, we'll translate those phonemes to visemes. So remember, the phonemes that's useful, but we can't use the phonemes to drive a 3D character. What we need are the visemes, the visual units of speech. So next we'll translate the visemes, and then we'll print out those visemes. Okay, so pretty simple. Let's run it and see what it does. Okay, so it looks like I found that word in the dictionary. The word was market, by the way. And so the set of phonemes you can see listed here, there's 1, 2, 3, 4, 5, 6 of those. And then translating those phonemes into visemes, there are 1, 2, 3, 4, 5. There's also 6 of those. So that's kind of unusual. Typically, you'll see that there are fewer visemes than there are phonemes. But in any case, these visemes, number 2, 3, 14, 4, 1, and 5, again, these are the ones listed here. These are the ones that we can use in our program to drive a face. So again, back to the particular model that you would use, for example, in FaceGen, you see the different phonemes listed here. Although, again, FaceGen calls these phonemes, but these are really the visemes. These are the visual units of speech. And also, again, what's missing, though, is the timing information. So we found the word in the dictionary, we translate it into phonemes, we translate it into visemes, but in addition to understanding what visemes to use, we'd also need to know the timing. So for example, viseme number 2, we would need to know as soon as we start playing the audio in our program, we would need to know when to start morphing that particular viseme and then when to turn it off. And then for viseme number 3, we would need to know when to start morphing it and when to turn it off. All of those times relative to the time that we started playing the audio. And so again, that's what is going to be returned by the other method that I mentioned, which I'll just look at that one more time and show you. So that would be this function here. Now, putting it all together, I'm skipping some steps, but hopefully you get the idea of kind of the workflow involved in generating lip syncing on a 3D character.